Thank you for joining us for today's Beyond the Basics webinar, Rolling Element Bearing versus Sleeve Bearing Diagnostics. Before we begin, I'd like to cover a few housekeeping items. At the bottom of your screen are multiple application engagement tools that you can use. All the engagement tools are resizable and movable, so feel free to move them around to get the most out of your desktop space. You can make a request to book a meeting or a demo directly from your console. Just click on the appropriate engagement tool and add your information. For the webinar portion, the slide area can be maximized to full screen by clicking on the arrows in the top right corner. If you have any questions during the webinar, please submit them through the Q&A engagement tool at any time throughout the presentation. We will try to answer these during our Q&A session, but if a fuller answer is needed or we run out of time, it will be answered later via email. Please know that we do capture all questions. I want to remind everyone that this webinar is just one in the series of planned webinars. If you have missed one or two, no worries. The related content engagement link in today's webinar can direct you to our on-demand site. While you are there, you can also download a copy of today's slide deck and link out to sign up for future sessions in the series. We would also like to ask you to take a few minutes at the conclusion of the webinar to complete our survey. This will help us bring more topics and improve on future webinars. During today's webinar, we have two instructors, Billy Wise and myself, John Kingham. I have been working with Bentley Nevada for over 35 years, and yes, while that picture is a bit old, it's not that old, and luckily all the hair remains. It's just a little bit grayer now. I started working for Bentley after a few years in the Gulf of Mexico doing directional drilling surveying work. The first 15 years or so with Bentley, I traveled extensively throughout the Northeast United States into South America and the Middle East, diagnosing machinery problems based upon their vibration characteristics. I then went into training and service management before landing in my current role as an application solutions architect about 15 years ago. In this role, I help to ensure that the solutions Bentley brings to our customers will solve their problems the first time. Billy Wise has been with the Bentley Nevada business for 10 years, and prior to that was an end user employed by a major petrochemical producer. He has over 25 years of experience in maintenance and reliability, and is mainly focused on the application of Bentley Nevada technology as it applies to rotating assets that utilize rolling element bearings. These include our Scout portables, Ranger Pro wireless, VB Online Pro periodic monitor, and Orbit 60, our latest continuous monitoring system, which has been designed with plant-wide and specifically rolling element bearing capabilities. So one of the first aspects that needs to be figured out is what sensors are we going to use for the different types of machines? As you can see here, the rolling element bearing really doesn't have much movement in between the case and the shaft. And that's because there's no clearance there. And all of that energy that is being transmitted through the shaft goes right to the case. So in this case, we're going to use case-mounted or seismic transducers. Whereas if you look at the proximity probe, you'll notice that the shaft is riding on a oil wedge, and most of the vibration is absorbed by that oil wedge. There's very little vibration that's transmitted to the case. In fact, typically it's around the order of 25% or so. So in the case of a fluid film bearing, proximity probes are the best. Okay, so let's talk about seismic transducers. Seismic or case-mounted sensors measure the movement of the casing relative to a point in free space. And from a velocity standpoint, spring coil and magnet transducers were the first of these sensors. I used to use them back in 1986 when I started with Bentley. And towards the later part of the 80s, early part of the 90s, we moved to more modern piezoelectric accelerometers that had a integration chip built right in, and those are velometers. And this was important because if you had an Excel and it had a fairly long cable run, when you integrate, the low frequency components get amplified significantly. So there's usually a little bit of low frequency noise hanging around. If you do the integration before it gets out of the case, the transducer case that is, you won't have that errors. So, but again, moving on, these velocity transducers used for situations where the vibration is transmitted to the casing, such as roller element bearings and gearboxes. We also use them on large steam turbines where we integrate that velocity signal to displacement, add it to the proximity value, and get absolute values. And as I mentioned in the introduction, seismic transducers cannot read the motion of shaft vibration very well in a fluid film bearing due to the oil acting as a vibration damper. Now, what I don't have on this slide that is very important for rolling element bearing diagnostics is that when you're doing diagnostics on rolling element bearings, you're probably going to use an accelerometer. Use velocity for protection, acceleration for diagnostics. And of course, here we have proximity probes. Now, what I want to point out in this picture is we've got probes and we've got a proximeter. What we don't have is an extension cable. And one of the things that's very important, and this is covered in our Back to Basics course, is that you need to have a matched system. So if you have a 5-meter proximeter and those look like 1-meter probes, you're going to need a 4-meter extension cable. Now, what would happen if you had an 8-meter extension cable? Well, you might still get a reading, but it wouldn't be very accurate. You wouldn't have a very good full-scale range, and your diagnostics would be way off. So, please make sure that you have a matched system. So now that we have covered sensor basics, let's start interpreting steady-state data formats. This is primarily going to be centered around sleeve bearings, and Billy will cover roller element bearings shortly. So here we have an orbit time-based plot. This is one of the basic plots that we use in rotor dynamics and diagnostics. I love to describe an orbit as basically if you put a pencil lead in the center of the shaft and you held a piece of paper up to it, that is what the pencil lead's going to describe, is that orbit plot. And because of that, you can visualize what forces are acting on that rotor. Okay? And when I present this plot in a seminar, I usually ask the audience, what is the shape of that orbit? Everybody knows that it's a circular, but nobody wants to raise their hand and tell me. But it is, in fact, circular. And then I ask, well, should it be circular? And, I get half yes, half no. Well, if this is a vertical machine, like a vertical pump, then maybe circular is okay. Possibly with tilting pad bearings in a horizontal machine, it might be reasonable to have a circular bearing. But if you look at the logo in the lower right corner of Bentley, Nevada, that is more typical of a horizontal machine with a gravity preload, kind of oval shaped. Okay. So when I have a circular orbit like this one, I have to imagine what are the forces that are acting on this. And if you can recall back to when you were a child and you had a bucket of water and you rotated it around and that water never came out of the bucket. So what was happening to your arm socket? Well, if you had a nice bearing, it would have been very circular because that water bucket was pulling your arm as hard as it could away from your shoulder. So in this case, it isn't unbalanced because I look at the speed and I see that it's 300 RPM. So 300 RPM is probably not going to be an unbalance. The other thing is I look at the amplitudes and they're in the 0.4 mil range. So this plot has been auto-scaled, and it probably ought to be manually scaled, okay? But this is the type of information that we want to look at when we're doing rotordynamic diagnostics. So on the last plot, we looked at an orbit time base, but we really only concentrated on that orbit portion. Now we're going to look at the time base. So on plot A on the left, you'll see that there are two key phasors in between two peaks, right? So each key phasor dot, that blank spot, bright spot, means that you've had a revolution of the shaft. So your primary vibration is not at 1 times running speed. And because we see two key phasor dots per sinusoid, you know that it's probably around half X or something less than 1X at any rate. But how do you know if it's locked into exactly half X? Well, that's kind of interesting in that if you can draw a line straight across and parallel to each other through the key phasor dots, then you know that you've got half X. Now, on plot B, we have two peaks for every key phasor dot. And those key phasors also line up in a straight line. So in this case, because we have two peaks per revolution, our vibration is known as being at 2x. Here I'm going to talk a little bit about fluid instability, and we're going to use the orbit time base as well as a full spectrum plot. As you can see in the orbit time base, there are multiple key phasor dots, and if you look at how they line up, they are not in straight lines. So they're not locked into half X exactly, but they are less than 1X, probably less than half X. If you were seeing this on an oscilloscope, I believe they'd be rotating with rotation. So the other thing about that orbit is that it is, again, very circular in nature, in shape. And that's typical of a fluid-induced instability, as the fluid is running around the bearing at the circumference and is allowing that shaft to go around the bearing as well. So it's very circular. We can look at the full spectrum down at the lower left, and you see that the big peak there, I've got 1X identified, is well below half X. Okay? So when you're looking at fluid instability, those are some indicators for it. So with the last set of plots, I introduced the concept of the full spectrum. And what we have developed and we found in the digitization of orbit plots is that there are positive components and there are negative components. The negative components tend to be related to frictional components, okay? And if you look at the center orbit, you'll see that if you have a vector A, and it is rotating counterclockwise, and you have a vector B that represents the negative components, and it is going to be rotating clockwise. So the major axis will be 2 times A plus 2 times B. The minor axis will be 2 times A minus 2 times B. And you'll see in a spectrum that the positive component will be 2 times A and the negative component 2 times B. We use these extractions in System 1 for decision support. They're available to you to use there as well, and it helps describe that orbit shape. One of the other plots that we use in steady state diagnostics is the full waterfall plot. And basically, the waterfall plot is a series of cascades versus time. Now, the data that I've been showing you is all from a rotor kit, and it's a rotor kit that's been set up to do oil whirl or instability. And you can see in this waterfall plot where the half X or slightly less than half X vibration comes into play. And that's where we've been adjusting the preload frame so that that bearing becomes unstable. But the waterfall plot is a great tool in diagnostics. Okay, now that we've covered steady state plots, let's do some interpretation of transient data plots. Transient data, in my mind, is data when the machine is starting up or shutting down. It can also be when the machine is changing states or loads, but for the purposes of this discussion, we're going to be talking about changing of speed. Well, here are the 4 basic transient data plot formats. My favorites are the polar, which is in the upper right corner, the Bode plot in the lower right corner, and the full cascade plot in the lower left corner. The shaft centerline plot I'm not going to spend too much time on, but it basically represents where the shaft is at different speeds and so forth. And it's a great plot for corroborating what you already think you know about what's going on with the machine. It is a plot that can be affected by thermal growth, and so on a startup, I'm not fond of them. Shutdowns, there's usually not much thermal growth taking place, so you know, it's probably good to use then, but still I don't hang my hat on that plot for a diagnosis. I go to the other plots and see what's going on with the rotor. One really neat feature about this particular shaft centerline plot is that you can see an orbit superimposed upon it. And again, I was talking about how we were using rotor kit data and how we had an oil whirl bearing on the outboard end and a spring-loaded preload frame that we could basically center the shaft in that bearing so that it was really susceptible to whirl. And you can see a very, very nice whirl orbit going on, superimposed on that shaft centerline. You can kind of see where we moved it, so forth. Over to the right, again, we have that polar plot. I love the polar plot. I use that for balancing, and it's very good for telling me where the resonances are. The Bode plot below it is also very good for figuring out resonances. The other nice thing about this particular plot, you see you have a green line and a dark blue line. Might be black, but that black line is a 1X. And you see that over on the right-hand side, it's the 1X and the direct do not, they don't coincide with each other. They don't track each other. It's not till you get around 4,500 RPM or so that they track really nicely. And that's what I like about looking at a Bode. I look at the direct and the 1X on the same plot, and I look to make sure that, 1X is a predominant frequency, okay? If you have something else, it's usually an indication that you've got something going on. Then that full cascade over to the left, you can see that you've got some less than half X going on. Okay, next one. So I've showed you the basic plots that we use in transient data analysis, but what is the information that's available from these plots? You'll find the slow roll speed range, and the Bode plot's great for that. The slow roll runout vector and compensation effect, the amplitude, the phase, and frequency of the resonance. Love the polar plot for that. Heavy spot, high spot relationship, and rotor mode shape and deflection shapes. We're going to go over those in the next couple of slides. So here we have a Bode plot. It's not the same Bode plot we had previously, and you can tell that by A, looking at it, and B, you'll notice that the 1x and the direct do correlate pretty well with one another. But what I want to show you here is that we can find the slow roll speed range and slow roll vector and so forth. So essentially, for the slow roll speed range, you're looking for the time when there's not enough, the rotor can't generate enough momentum to really be vibration. So what you're seeing are, glitch and run out of the shaft. So typically you're going to look for a flat area on the phase. There's not much phase change and there's not much amplitude change. So here we've got our slow roll speed from about 0 to 500 RPM. You see how nice and flat that is, and then we can use the scales to figure out what our amplitude and phase is. So our slow roll is going to be 1.4 mils peak to peak at 235 degrees. Okay, so here we have a Bode and a polar plot, and they both have, slow roll issues. But I want to show you which one is easier to compensate mentally, okay? So here we've got 360-degree phase shift. How are you going to figure out where, your resonance is? Because you're looking for that peak and 180-degree phase shift. Here you got 360. Same on the polar, although it's much easier on the polar. So if we compensate that, now you see that you do have that 180-degree phase shift, and your peak is where it should be. On the polar plot, you start at 0, and the heavy spot is the high spot below the resonance, and the heavy spot is 180 degrees from the high spot on the after you get through the resonance. So here we have a heavy spot of around 240, 245 degrees. So where am I going to put my weight? I'm going to put that opposite that at 60 or 45 degrees. Okay. And above the resonance, my high spot is opposite the heavy spot. My high spot is at that 45 degrees. So they both correlate and tell me where to put that balance weight. Again, I have here 2 more examples of why a polar plot is easier to mentally compensate than a Bode plot. In case 1 here, where your polar plot basically makes a circle that's equidistant around the origin, your amplitude is going to be a straight line, and your phase lag is going to be a sinusoid. I'm sorry, not a sinusoid, but a big drop like that. You may not even think there is a resonance there, right? Very difficult to tell. And then in case 2 over here, you're just in one quadrant and your amplitude is going up and down. So actually it's going to go down and up. So this is what that's going to look like. Again, very difficult to figure out where your resonance is, how bad it is, etc. Wouldn't want to have to balance off of a Bode plot. Okay, now we're going to talk a little bit about the balancing effect. The large polar plot lines are the before balancing. I put a weight somewhere around 270 degrees against rotation, right pretty much in line with the key phaser on that left plot. And it was a good amount of balance weight, and you see how the vibration came down at all areas of the polar plot. So great effect on that That's one of the beautiful things about using polar plots for balancing. And then if you go in and join us in one of our machinery diagnostics courses, we can teach you about how these vectors tell you where to move the weight and how much more or less weight to add and so forth and so on. It's pretty interesting stuff. I used to do this again for like 15 years and always found it, satisfying and a challenge. Here I just want to talk a little bit about typical flexible rotor mode shapes. The polar plots that we just saw were first mode polars, and if you looked at bearing 1 and bearing 2, they'd be in line with each other. So if you printed out a plot from the left and bearing and one from the right bearing, held them up to the light, they would pretty much overlay very nicely. They'd be in phase with each other. And those are called first mode. There's no nodes between the bearings. Then you will have steam turbines, in particular, generally are working in the second mode, where there's a node between the bearings. So you go through that first mode, and then you'll have a second mode. And there the polar plots will be 180 degrees out of phase with each other for that second mode. Okay? Again, I'm going to show you a polar plot in a moment. It'll show you that. In my experience, I never really got into any machines that were in the third mode. Some generators will get close to being in the third mode. Those are really, really good luck at balancing those, unless you're in a balance pit. Okay? Very difficult because you have to put weights where you can't put weights. Okay, let's talk about translational and pivotal resonances. It's first and second mode, and I apologize, this slide didn't build the way I wanted it to. But you'll see the inboard is on the left and the outboard is on the right, so we're on opposite ends of the machine. And the yellow highlighting represents the first mode, so the first balance resonance, the pivotal resonance. And the blue represents that translational or the second mode. And you see that on the inboard, they're opposite each other, and on the outboard, they're right in line with each other. So let's look and see where the heavy spots are. So our first mode heavy spot, right up at the top, like top dead center on both ends. And that makes sense, right? And then the second mode heavy spots, slightly off, 180 degrees from each other between the inboard and the outboard, but you'll see that on the outboard, they're still within 45 degrees of each other. So if I were a betting man and I was doing my balancing, I would put a weight in about 180 degrees opposite, so at 180, somewhere between 150 and 180 degrees on that outboard side, and I'll get the best bang for my buck there. So we've covered a lot of information in those few plots. The total speed range, the run-out vector, how to compensate for it, both physically and mentally, the amplitude, phase, and frequency of the resonance, the heavy spot, high spot relationship, and the rotor mode shape and deflection shapes. Now, we could have also gotten the synchronous amplification factor and looked at structural and split resonances. We don't have time for that in this webinar, but if you go to the MD course, we'll cover that as well. So let's move on and look at shaft centerline plot and see what we can find out about preload identifications. So here's our shaft centerline plot. Again, this is our orbit time base. We're back to our favorite whirl orbit, and you can see it transposed on our shaft centerline plot. We also have, if you look closely, you'll see the green is a small orbit back when the system is fairly well pressed against that wall, and also that orange orbit. Again, we've moved the preload frame so that it is kind of against the wall of the bearing, so it's kind of constrained. And that's what you're going to find when you look at the shaft centerline plots. Is the shaft where you expect it to be? Like that orange one, I wouldn't expect to see my shaft above the center line or the split line of the bearing. So that would be odd. I'd look at the shaft center line of the plot across the coupling. Is it down at the very bottom? So that shows me it's constrained. You have to use these shaft center line plots with other plots to correlate what your belief is going on in that bearing. Okay. Okay, so we have just looked at preload identification. We used the shaft centerline plots for that. Now let's take a look at frequency relationships. And for frequency relationships, I like to look at cascade plots. We're going to look at horizontal and vertical relationships. Cascade plots. So here we have two cascade plots, and cascade plots are spectrums versus speed, and we've got a bowl gear and a pinion gear. And you can see that there's something going on about 17 hertz. Turns out that's the torsional natural frequency for the bowl gear. And as the rotor, as the bowl gear goes through that, it excites that 17 hertz on the pinion cascade. So that's not really running speed of that pinion cascade, but it is affected. So when I'm looking at cascade plots, I'm always looking at horizontal and vertical relationships. Okay. Okay, now this is a pretty interesting cascade plot. You'll see that the cursors are correlating or synchronized rather, and so the on the 1x plot, the Bode plot on the right, you'll see that we're pretty close to the resonance. You'll see that peak, and then if you look at the cascade on the left, you'll see that the subsynchronous is going to transition from whirl kind of into whip. And whip is when that rotor locks into the first balanced resonance. And you can see that the whirl goes up at an angle, and then it kind of makes a turn, and it's going to become asymptotic to that resonance. And when that happens, when the machine goes into whip, you can have some major catastrophic damage because it is exciting a frequency that it wants to vibrate at, and you can wreck a turbine with this. So if you get into a situation like this, you want to make sure you shut that machine down as quickly as possible. Okay. Okay, we've reached the rolling element bearing portion of the diagnostics presentation, and now I'm going to turn it over to Billy Wise. Take it away, Billy.
Thanks, John. So as John mentioned, our next topic for this presentation will be focused on the specifics of rolling element bearing diagnostics. As John has already discussed, the sensor of choice for machines with rolling element bearings is the seismic sensor. More specifically, when we're talking about diagnostics related to these types of machines, we're referring to accelerometers. It's important when discussing the use of accelerometers for diagnostics that we pay very close attention to the placement and mounting techniques used for these types of sensors. This is because accelerometers are designed to be able to accurately measure amplitudes out to a particular frequency. In the image on this slide, mounting techniques are shown, worst to best, from left to right. As we move from left to right, we see the highest dependable frequency increased until we reach the stud-mounted approach, which yields the maximum frequency response of the sensor. This is especially important when we start to discuss the use of early rolling element bearing defect detection algorithms, such as demodulation, because the signals for these defects are typically very high, and if we choose the wrong mounting techniques and attempt to apply these tools, we may jeopardize our ability to effectively see these defects. Also, surface preparation is just as important because things like paint, rust, or rough surfaces can cause attenuation or reduction in amplitude of the signals that we are hoping to capture. Shown here are some of the machine faults commonly identified for rolling element bearing machines using some plot types that we will discuss in upcoming slides. Faults like unbalance and eccentric rotors or bent shafts, misalignment conditions created when machine shafts are not collinear or when belt drives are installed improperly, looseness both due to installation or improper fit and saw foot conditions, defects inherent to rolling element bearings themselves, gearbox component faults, flow-related issues like cavitation and turbulence, motor-related electrical faults, and resonance. The first plot type that we will cover for rolling element bearings is the waveform plot, which is amplitude versus time. This plot type is representative of the movement of a machine with respect to free space. It is a summation of all frequencies present at the machine as indicated in the image to the right. It represents the back and forth motion of the machine from the perspective of the sensor and is recorded as a continuous series of positive and negative values that correspond to the engineering units of the sensor type we use to capture the vibration. For rolling element bearings, as mentioned previously, this will be captured using acceleration, as this domain is the most sensitive to high-frequency events typically associated with the machine with this bearing type. Two key parameters that we measure are the waveform peak-to-peak and the crest factor values. These are very helpful indicators of bearing and gear health and are also used to highlight the presence of cavitation in pumps. Shown in the image to the right, the waveform peak-to-peak is a measure of the difference between the maximum positive and maximum negative amplitudes that are present in a waveform sample. Alternatively, the waveform crest factor measurement is calculated by dividing the peak amplitude by the RMS value. Since perfect sine waves have a crest factor of 1.414 and no impacting, we can imply that as we exceed a crest factor value of 1.414, it indicates that there is a level of impacting present. Again, impacting is important because it can indicate either metal-to-metal contact or cavitation in pumps. We trend these values over time and can use alarm set points to alert us when something has changed so that we can apply focus only when necessary. Another tool that we have available is the ability to overlay fault frequency markers on the waveform to help positively identify if a particular fault is present, an example of which is shown here. We can see what appears to be impacts present in the waveform to the right. By overlaying fault frequency markers, we can positively identify that these impacts coincide with running speed. Sometimes, it can also be helpful to integrate a sample after it's been captured for diagnostic purposes. By this I mean that if a waveform was captured in acceleration, but we need to view this sample in velocity, we can simply use the software to convert it so that we can see it in that domain. As shown here, we're now viewing this sample in the velocity domain, which can be helpful when trying to diagnose faults like misalignment, for example. Another handy tool is the ability to switch the x-axis units between time and shaft revolution. This gives us the ability to quickly compare how events are occurring in the waveform with respect to shaft speed. The next plot type we'll discuss is arguably the most used in rolling element bearing diagnostics. It's the spectrum or spectral plot. It is charted as amplitude versus frequency, and it's important to note that this plot can exist without the plot we just discussed, the waveform. This is because the spectral plot is derived from the waveform using an algorithm called the fast Fourier transform, or FFT for short. This plot type is important because it gives us the ability to separate out the individual frequencies that are present in the waveform. This is extremely helpful, as once we know the shaft speed, we can relate the individual frequencies to that speed and use that to determine what could be the potential cause of the vibration at the machine. We often view the spectrum in the velocity domain, integrated from an acceleration signal, since this domain generally treats amplitudes equally across the frequency regions that we are most often interested in. A common process that is used with spectral plots is to break them up into segments or spectral bands that correspond to forcing functions that could be present in a rolling element bearing machine. We use these spectral bands as a source of trended variables to which we apply set points. These trended variables help us to quickly identify when the machine is experiencing a change and ideally makes our workflow easier to manage. To make analysis easier, we have cursors available that can be used to quickly identify frequency components by hertz, CPM, or orders, and the amplitude of the components too. These are invaluable tools, and they come in three major types: the single cursor, the harmonic cursor, and the sideband cursor. They all play an important role in analysis and make quick determinations easy. As with the waveform, we also have fault frequency markers available to us in the spectral world too. These are extremely helpful when trying to identify where a frequency or family of harmonic frequencies are related to bearing defects, looseness, gear components, etc. Since we are discussing rolling element bearings, I'd like to point out the specific frequencies in which we are interested with regards to these complex components. There are four general frequencies that we use for fault identification: the cage, ball spin, outer race, and inner race frequencies. These frequencies can be calculated manually if we know the specific measurement characteristics of the bearing, but lucky for us, there's a database available with thousands of bearings pre-populated for use in our condition monitoring tasks. Now that we have these frequencies, we can quickly identify what component in the rolling element bearing is causing the vibration. This is important as it gives us a better indication of how to react. An inner race defect is more severe than, say, a cage defect, and we can act appropriately. As we see in this slide, there's impacting present in the waveform that corresponds perfectly with an outer race defect. This will also be present in the spectral plot, as shown here. Along with bearing defect fault frequency markers, we can also utilize other markers for running speed harmonics, electrical motor issues, vane or blade pass, and gear-related frequencies. Another tool in our tool bag for rolling element bearing diagnostics is demodulation. Demodulation is used to identify bearing defects well in advance of when they could be seen easily by the naked eye. When using demodulation, we need to pay special attention to mounting techniques and placement, and we also need to have a general understanding of the machine as well. If we see defects present using this methodology, normally we won't take action, but rather may choose to increase data collection frequency to keep an eye on the defect advancement and use this information to plan for appropriate action in the future for our convenience. Rolling element bearing defects first appear as very small impact events that excite the natural frequency of the bearing and its supporting structure. This natural frequency is high in nature, and the impact events created by the defect are very small and are typically drowned out by the dominant lower frequencies present in the vibration signal. The demodulation process, simplified greatly, involves three basic steps. First, we apply a bandpass filter to the sample, which effectively eliminates the dominant lower frequencies. Next, we use a low-pass filter to strip away the carrier frequency, which leaves behind the modulated signal associated with the bearing defect. Lastly, we apply the FFT process to the remaining waveform to reveal the individual frequency components, which help us to identify which part of the bearing is beginning to fail. The last plot type that we use with rolling element bearing diagnostics is the trend plot. Equally as important as the waveform of the spectral plot, a phrase that I often use is "the trend is your friend." This plot helps us to evaluate amplitude over time, and it's how we visualize things that we've discussed thus far, like waveform peak to peak, crest factor, or spectral bands. This plot type is also helpful when we're trying to correlate vibration trends to process conditions that can often negatively affect the condition of a machine. This now brings an end to the discussion on rolling element bearing diagnostics and will now lead into questions.
Okay, we are now at the Q&A portion of the program. If you haven't already, please type your questions into the Q&A panel. Bring that up. Okay. So our first question is, does Bentley Nevada have any portable vibration data collectors? Billy, can you go ahead and take that?
Certainly. Yeah, so Bentley does offer two different types of vibration data collectors. We offer a what may be considered the industry normal one-piece design, which includes the graphical user interface and how you interact with the devices all in one piece. And we also have a two-piece design as our newest product, which includes just a analog to digital conversion device that communicates with a smartphone via an app using Bluetooth technology. Yeah.
Okay, cool. Let me push this. So the question is, what are translational and pivotal resonances? It has been a long time since I've studied that, but my recollection is that translational and pivotal are essentially the same. My apologies. I think my phone got hung up on. I'm not sure where I left off, but I do have a question here on where can I find the list for bearing fault frequencies. Billy, can you handle that? Okay, so I'm wondering, I see that somebody else has lost sound.
Hey, John, this is Gina. Hey, John, this is Gina. The audio is back on for the audience, so Billy might just be disconnected. You might have to answer a few of the questions till he gets back on.
Yeah, sure. Okay, great. Glad we're back on. So we're, Billy, you back on?
Yep.
Okay.
So the answer to that question, is that bearing fault frequencies can be found via our System 1 software in our configuration portion of that software. We have a database that's available that has thousands upon thousands of bearings that are already predefined. In some instances, if by chance there isn't a bearing in that database, we also have the ability to preload the characteristics that I talked about in the slide so that they can be automatically calculated for you.
Okay, thanks. Okay. What are some common non-oval shaped orbits, and what failure modes or rotor issues do they represent? We recently had banana shape and figure 8 orbits and found that it was because our coupling key was too long. That's interesting. Wondering if there are other shapes to look for and what they mean for diagnostics. So, I think as I explained, if you think of an orbit as putting a piece of pencil lead in the center of the shaft and holding a piece of paper up to it, that's what it's going to draw. And from that, you can see what the forces are. Typically, when we see banana shape or figure 8, that tends to make us believe that you have a misalignment. I'm curious about this coupling key. And maybe the coupling key was locking the coupling, which then makes any kind of misalignment, it exacerbates it, amplifies that effect. So typically when another thing that I look for when I'm looking for misalignment, you'll have kind of a flat orbit on one side of the coupling and a very round orbit on the other side of the coupling. And that's because that round orbit isn't supporting much, and that flat orbit is supporting more than it's designed to. So, going to our machinery diagnostics class, you'll be exposed to a couple other types of orbit shapes, but it's not something where you can make a chart and say if you have this, you have that. So, next question is, what classes does Bentley offer on these topics? So the first class that I would recommend to anybody is our MD class, Machinery Diagnostics. And that is a 5-day course. And one of the beautiful things about our courses are they tend to be hands-on, a lot of hands-on stuff. So half of those for 5 days are workshops, and you actually go in and play with the rotor kit. You learn how to balance and so forth. There's Applied Diagnostics Workshop, which is the next level above that, where we have case history data, and it's your job to solve the case history. And then I think it's every other year we do an advanced machinery diagnostics course. Billy, can you help with the rolling element bearing courses that we offer?
Yep. Yeah, so we also offer specific training for portable data collectors, and we also offer a specific System 1 for portables or System 1 fundamentals training as well, where we go through, how to set up machines, how to configure measurements, everything associated with the portable.
Okay. So somebody asks, is there a document that shows orbits and possible faults? And I'm not aware of one. And again, because of the different forces that are acting on an orbit, no two orbits really look the same. And it's not like 1x. If it's 1x, it's this, because there are multiple different malfunctions that manifest themselves as 1x. So let's see. Next question is, please confirm how much energy is absorbed by lube oil film and fluid film bearings. So I think I stated that typically if you have a prox probe looking at a shaft and you also have a velocity probe on that bearing cap, you'll probably get 1/3, a quarter to 1/3 of the energy is showing up in the seismic. So the balance of that is what is being absorbed by that oil film. So, 3/4 of it to 2/3. Okay. Let's see. I have somebody who couldn't hear the answer to the motor fault question and still cannot hear. Hopefully they can hear at this point. And so I think I'll make this our last question. Billy, the question is, does Bentley have any courses that teach balancing? And I just mentioned that our MD course, Machinery Diagnostics, does have, we spend, I think, at least a day on balancing single plane and multiplane.
And we also have a balancing specific class, Advanced Field Balance, now via the Bentley training website. That's a 5-day course that effectively spends a full 5 days on field balance. It's also touched upon in the portable training as well. It's touched upon briefly.
Okay, great. Thank you, Billy. Excuse me. And thank everybody for attending today's webinar. If you have any additional questions or would like to receive professional development hours, please contact your account manager. If you would like to learn more about using System 1 or Machinery Diagnostics for that matter, and are interested in attending one of our formal courses, please visit www.bentleytraining.com. And judging from the questions, there's quite a bit of interest there. And while we are starting to offer several courses in person, thanks to COVID, we have pivoted and we are making some of these training courses online as well. They're still instructor-led. You still log in at a prescribed time. Excuse me. There's still rotor kits involved. We put cameras on them. You tell the instructor where you want to put your weights and so forth in the balancing portion and so forth. If you would like to watch a replay of today's session or suggest it to a friend or colleague, you can find a link in the Related Content tab on your console. I will caution you, however, that the replay won't be available until at least half an hour from now. In the meantime, the Related Content tab also includes registration links to our future webinars, as well as a PDF of today's training materials. Excuse me. One note on the PDF. Since what we did today was live, using some old notes here. But you can log back in here later to get to the Resources tab. And you can do that by clicking on the link in your original calendar invitation. One last but important thing, a survey will pop up on your console after the webinar concludes. Please fill this out as we value your feedback, and it was in fact because of this feedback last year that we launched these Beyond the Basics webinars. Again, thank you for attending and have a great rest of the week. Take care.